Jack Jackson back again with our series of review exercises from Unit 1, Descriptive Statistics. This video, we will be going over exercises 16 through 20. So, review exercise 16. Explain what a Pareto chart is and how it is used. Work this out and come back and check your answer here in just a second on the next slide. Press pause now. A Pareto chart is used with nominal or categorical data. It's a combination of a frequency or relative frequency bar graph with a cumulative frequency or cumulative relative frequency ogive. The bars are arranged in decreasing order of height. The ogive will then be concave down. Often the scale on one side will be actual counts, frequencies and cumulative frequencies, and the scale on the other side will be percentages, relative frequencies and cumulative relative frequencies. A Pareto chart is used to identify the significant few items which account for the majority of the total items. One example where a Pareto chart is used is identifying problems, such as types of defects in a manufacturing process. See the next problem for an example. So this is an example of a Pareto diagram, Pareto chart. Notice that we have our bars in decreasing order. Sometimes others category could be slightly larger than the one before it. It's always put last. Notice that we have a scale here of actual numbers here on this side. So these are frequencies and relative frequencies on this side, and frequencies and cumulative frequencies on the left. Relative stuff on the right side, percentages. Relative frequency and cumulative relative frequencies read on the right. Here we have a title. We have our different types of problems, defects, in decreasing order, and we have our broken line graph increasing from 0 to 100%. Our ogive, our cumulative frequency or cumulative relative frequency line graph, which is what an ogive is. All right, so see if you can read this one now. How many total defects did they record for the process? What was the largest sort of defects for this process? How many of those occurred, and what percentage did this make of the total? Where should the company focus improvements efforts? Explain and quantify. Press pause now. Well, there are 90 altogether. How can we see that? Well, a couple ways we can see that are that the total amount goes up to that line right there, which is a count of 90. So that's the easiest way to see it. What was the largest single source of defects? That would be scratches, which accounts for about 45 times, or let's see, about 50% of the total, exactly 50% of the total defects. So the most frequent defect was scratches, which occurred 45 times, amounting to 50% of the total defects. Where should it focus its improvements? Explain and quantify. If they could just eliminate the scratches and the dents, together that takes care of 70 of the 90, or about 78% of the total defects. So they should, no, not quite 70 of the 90. 65 of the 90, but 78% of the total defects, which you can see here, almost 80% of the total defects. So if they could focus on those two problems and fix them, they fixed nearly 80% of their total problems. So that's what they should do. So this is why you use a Pareto chart, is to take something that doesn't have an inherent order here to it, categorical or nominal level data, and put it in order so that you can find the significant few versus the trivial many. Exercise 18. List in order from most popular to least popular and define the 5 measures of central tendency discussed in this unit. List the 5 measures of variability discussed in this unit, and list the measures of relative standing discussed in this unit. Press pause now. Well, the 5 measures of central tendency we studied were mean, median, mode, mid-range, and mid-quartile, and those are in the order of most often used. Mean is the most often used. Median is also used very, very often. In fact, it's really good to report both of those two values. The mode is a little bit less used than those two, but still quite often used. The mid-range and mid-quartile are used a lot less often, with the mid-quartile being very rarely used. List the 5 measures of variability: standard deviation, variance, mean absolute deviation, range, and interquartile range were the ones that we studied. And list the measures of relative standing discussed in this unit. Extreme values, quartiles, deciles, percentiles, and z-scores were the ones we studied. Exercise 19. What does it mean for a measure of central tendency to be resistant? And which measures of central tendency are resistant? Press pause now. So the term resistant means resistant to outliers and extreme values. A measure of central tendency is resistant if moving an extreme value or adding an outlier has little or no effect on the measurement. So which measures are resistant? The mode, median, mid-quartile are all resistance to outliers and extreme value. Only in the most unusual circumstances are any of these, either any of these 3 measurements changed by moving an extreme value further out. In contrast, the mean and mid-range will be drastically modified if an extreme value is moved much farther out, so they are not resistant. All right, here we have 6 different distributions. 3 are given by histograms and 3 are given by box plots. Please comment on the shape of the following distributions. So in data set A, we see a bar here at 12 going up to 10, then a bigger bar at 13, then it goes, the next one's about 11, and the bars get shorter and shorter as we go on out, to the highest one being at 19, but only a height of 1. That's data set A. Data set B has the largest bar in the middle, with the bars going down as you go to both sides. Data set C has the highest bar at 8, and the bars get lower and more spread out on the left, but higher, lower than 8, but not coming down as fast on the right. Okay. See if you can make sense out of these here. So comment on the shape. Press pause now. So in data set A, we see the longer tail to the right. The data is kind of bunched up more on the left with the longer tail to the right. We call that skewed to the right, or positively skewed. Data set B is symmetric, or almost perfectly symmetric. It's more or less a mirror image about the middle. So if you look to either side of 4, you've got bars roughly the same height next to that. At 3 and 5, at 2 and 6, they get a little shorter, but they're roughly the same size and smaller on the end. Now, it's not perfectly symmetric, but it's mostly symmetric. So we would still call that a symmetric graph. Data set C, on the other hand, is a little more skewed to the left. You see more of the data bunched up on the right and a longer tail to the left. This is the direction of the longer tail is the direction of the skewness. So this is negatively skewed, or skewed to the left. Okay, now how about these box plots? How can we tell from that what's going on? Well, data set D is symmetric. How can you tell? Well, if you look, the box, the median is in the middle of the box, so that the size of the second and third fourths are the same widths. And similarly, the width of the lowest fourth, from the bottom whisker up to Q1, from the minimum to Q1, is about the same distance as the top whisker, that is from Q3 up to the max. So that's a typical picture for a symmetric distribution. Contrast that with data set E, which is skewed left. From here we can see that the top fourth is smaller than the bottom fourth, and the second fourth here in the first part of the box is bigger or wider than the next fourth, the third fourth there. So the median is more towards Q3 than it is down to Q1. The mean would be to the left of the median here when we have a long tail to the left. So the longer tail is on the left, that's skewed left or negatively skewed. In contrast, data set F is skewed to the right. You can see that the longer tail is on the right side. We'll pick up with this one on the next video.